13.1 The Ideal Gas Law. The Ideal Gas Law. So, Gay-Lussac measured the volumes of gases before and after a reaction. He devised the law of combining volumes. So, when gases react, the volumes of the reactants and products measured at equal temperatures and pressures are always as whole number ratios. So, what we're looking at right now is that we can utilize the numbers we use to balance an equation as the numbers used, as volumes of gases. So take, for example, this here. I don't know, do I have an equation of this broken down? Well, let me just write this out. So here we've got 2 volumes of hydrogen gas. So that's what we mean, 2 volumes of hydrogen gas reacting with 1 volume of oxygen gas to produce 2 volumes of water. So notice that the numbers that we're using to balance this equation can be utilized as volume units. So here you can see where, we're eventually going to see the mole ratios working in our favor to get to the stoichiometry component of gases. So Avogadro combined both Dalton and Gay-Lussac's ideas and related the volume of gases to the amount that is present, calculated from its mass. So Avogadro divided Dalton's mass ratios by the molar masses of the elements to obtain these mole ratios. So he realized that the mole ratios were no different to the volume ratios. So the mole ratios we learned back in Unit 2 and the gas ratios or the volume ratios, according to Gay-Lussac, no different. No different whatsoever. That we can use those mole ratios to help us with volumes as well. So here we have another equation dealing with gases. So we've got 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to form 2 moles of ammonia gas. But we can always also look at them as 2 volumes, or 1 volume, right? 1 liter is equivalent, will require 3 liters of hydrogen gas to produce 2 liters of ammonia gas. So here we have what is referred to as Avogadro's law. This is different from Avogadro's number, right? Avogadro's number, right? The 6.02 times 10 to the 23, right? That's not what we're talking about. We're talking about Avogadro's law, and Avogadro's law is looking at the volume of a gas with the number of moles present of that gas. But be aware, though, up until now, we've been talking about gases containing the same volume of its container. But the one thing now that we are going to look at is so up until now, what we're looking at is we've been assuming that the volume of a gas is based on the container. And that the volume can change if the size of the container ever did change as well. But right now we are kind of going into looking at, wait a second, gases do in fact have a specific volume, and that we can't have a 0 volume for a gas. But mind you, if we do have a 0 volume for gas, we're assuming that now that gas has condensed into a liquid, hence the reason why if we've got a liquid, we don't have a gas anymore. But anyhow, here is the formula for our volume and number of moles. And understand that there is what is referred to here, as we saw before, a direct proportionality. Direct proportionality, meaning if the volume of a gas goes up, in order for the volume to go up, so do the number of moles, right? So we can't just take a gas that's in a 5-liter container, pour it over into a 10-liter container, and say that the gas is now 10 liters, as we were stating before, as the assumptions that we were stating before. Right, these so-called ideal gases, right? But now we know that, no, wait a second, gases do in fact have a distinct volume, and that volume is directly based on the number of moles of that gas. And if that volume was to go up, the reason why the volume would go up is because the number of moles of that gas also would increase. Okay, so we have what is referred to as the molar volume, and this molar volume is based on one or however many liters for every 1 mole of that gas. So we can find molar volume of a gas by dividing the volume by the number of moles present. Okay. So if we look at the molar volume of an ideal gas, understanding that there's a difference between what's referred to as an ideal gas and what we're eventually going to see as being a real gas. Okay, so in an ideal gas at STP, the molar volume, okay, so sometimes if you're getting a question using ideal gas law that we're going to see in a moment, and you're being asked for STP, understand that the volume is always going to be 22.4 liters for every 1 mole of that gas. Okay, so if you look at it here, I've got 5 different gases here that I state. I'm demonstrating for 1 mole of that gas. Okay, we've got that many particles. Or molecules, should I say. Here are molar masses, but if you look at their molar volume at STP, STP is at 0 degrees Celsius and 101.3 kilopascals, or 1 atmosphere, or 760 torr, or millimeters mercury, whichever unit. All of those are interchangeable for pressure. That their volume is 22.4 liters for every 1 mole of that gas. So the volumes of real gases now, ideal gases have a volume of 22.4 liters at STP for every 1 mole. So scientists have decided that this is an acceptable approximation for any gas at STP using gas laws, provided that we are at STP, so that STP condition. If we are not at that STP condition, that volume will in fact change. So, real gas derivatives. At STP, most real gases behave just like ideal gases. Okay. However, one thing we know about real gases is that real gases will actually have a definitive number of moles. Okay, and that they will have a volume that can change if the number of moles changes. However, at high pressures or at low temperatures, gases no longer behave ideally. So in terms of the ideal gas, really at STP, all gases pretty much behave like an ideal gas. So one thing to recall from 12.1 were the following. Okay, so we are revisiting the kinetic molecular theory as I stated in 12.1. Gas molecules have an insignificant volume of their own. Molecules have no attractive forces between each other or with their container. Molecules move perfectly straight lines, and collisions are completely elastic and thus do not use up any energy. However, these characteristics led to the ideal gas. However, particles of real gases actually do have a significant volume. Molecules do attract, as we saw last class, where even non-polar molecules will attract one another. Molecules do not necessarily move in straight lines. And finally, collisions are not completely elastic in terms of how they redistribute their energy as they move about. So, at high temperatures, low temperatures, gases have small volumes, right? Makes sense, right? Greater the pressure kind of compresses the volume. At low temperatures, right, we don't have as much volume. Think about if you were to blow up a balloon. If you got a balloon, you could test this theory out. Put it into your refrigerator or freezer, come to it in an hour, and you'll see that balloon will have gotten smaller. Okay, it is no longer true to say that molecules have no attractive forces between others or their container, because they do. Right? Remember that uneven, that asymmetrical redistribution of positives and negatives. Okay, so we can no longer ignore the volume of gas molecules. So we are now going to see that we can't ignore the volume of a gas, because now we are going to look at also the number of moles that are present in that gas. Okay. So just a summary of what I just stated. So here is the next equation to know. PV is equal to nRT. When we visit stoichiometry in the next in the coming chapters, okay, this, when we're dealing with gases and we're being asked to find pressure or volume or temperature, in fact, we are using this formula. Okay, understand that Boyle's law, Gay-Lussac's, Charles's law, right? All those, the combined gas law. Okay. Okay, so these laws are not used in stoichiometry because we're looking at initial and final conditions. Typically in the stoichiometry that we're going to see, this is what we're going to be looking at when we are trying to find either pressure or volume. You might be wondering, where's the final pressure, where's the final volume, where's the final temperature? You're not going to see it because we're talking about a specific state, a place in time of that chemical reaction. And the one number that we're going to be introducing today is this gas constant, which is our R value. You'll memorize it, or you'll have it with you for the evaluation. So typically I ask students to calculate that R as a foolproof way of remembering it. So in an evaluation, if they ever forget, try to solve this problem by isolating for R from this equation. So if I isolate for R, I bring everything over. So I have my PV and my N and T get dropped here at the bottom. So when I'm bringing this over, it becomes division. Okay, so here is the calculations. So when you're finding this R value, okay, and again, this is what you're going to use. So you're using this R value here for all ideal gas law equations. Okay, so whenever you're using this PV is equal to nRT, this is going to be your R value, provided that your pressure units are going to be in kilopascals, your volume is going to be in liters, and of course, temperature is a given. It's always going to be in Kelvin. Okay, so this is a number that you are going to be using for your R value. And you can calculate it by throwing all these numbers into this equation. Okay, and if you'll notice here, the units are pretty tricky. The units for R, I don't expect you to show all these units, but if you do include them, they're easy to kind of follow when you're crossing out units in your calculation, so you know which unit your final answer is going to be in. But I'm not going to be picky about that in the evaluations for this coming culminating that's coming up on Wednesday. Anyhow, guidelines for using the ideal gas law. So here are a few guidelines. Always convert temperature to Kelvin. This is a given. Okay, this is a given. Okay, this is a given. You never, ever, ever use degrees Celsius in any of your calculations, please. Okay, the minute you do that, I am telling you right now, your answer is going to be completely wrong. Try any of the sample problems. Try any of the homework questions. Put degrees Celsius, and you'll see you're not going to get a number anywhere near the numbers that the answer is. Okay. Now, masses, right? You might be asked, here's a formula of something. Here's, okay, find carbon dioxide gas. Find the pressure of carbon dioxide gas. So you know carbon dioxide gas. You can find the molar mass, right? You might be given a mass of it. While you're using the mass and molar mass, it'll help you find that N value, right? Just like we did in Unit 2. Next thing, make sure volumes are always in liters. Understand that typically I give units in milliliters, but that's because that is measurable. Milliliters is measurable. Okay, so this is for measurement. Okay, and liters is for calculations. Okay. Now, when using the ideal gas law, it will be easier to always convert pressure to kilopascals. So if the question is giving you in torr or in millimeters mercury or in atmospheres, make sure that you convert the P value, the pressure value, to kilopascals to use the ideal gas law formula. Because if you look at, here is that R value. Okay, so here's the R value. This is a constant that you use in these calculations. This is the R value in PV is equal to nRT. Now, notice what the units are. Kilopascals, liters, moles, Kelvin. If your P value is any different, your liters are in milliliters, your moles are in, I don't know, grams, or your pressure, your temperature is in degrees Celsius, you're not using this R value. In fact, the R value is different if we were to change this kilopascals to torr units. So torr dot liters / moles Kelvin. Okay, so understand that there are different R values based on the different pressures that you can use. But we are going to make things simple. And our R value, we are always going to want our pressure units to be in Kelvin. With regards to the this coming culminating, I think I try to make sure, like, so when you'll see a gas question that you're going to use the ideal gas law, hint hint. The R value, you're going to be using this as is. There's not going to be any conversions. Okay, but in terms of conversions, what you will typically see, as you might see on today's test or tonight's test or Wednesday's culminating, I might ask you to convert milliliters to liters. Okay, but aside from that, maybe on a multiple choice I might ask on Wednesday. But in terms of the short answers, I'm trying to keep things relatively straightforward. So let's look at the sample problems. Okay, for these. Okay. So the first question: what is the volume of 3 moles of nitrous oxide at STP? Know that at STP, here's the volume, 1 mole, right? So we're given 3 moles. So how do we go from 1 mole to 3 moles, right? So what is the volume? Volume is going to be tripled. So we substitute it into the Avogadro law equation, isolate for our final volume, and we get V is equal to 67 liters. Okay. This pretty much, again, just reiterates what we just did in the first sample problem. 44.8 liters. Okay, at STP, how many moles are present? Well, now we're isolating for our moles, and we get 2 moles, right? And if you look at it, you can almost figure out, right? 44.8, 22.4 liters, they've doubled it, right? So double the number of moles. Now, question then continues, what is the mass of this gas? Well, we know that methane gas is CH4, so find the molar mass, okay, of CH4, and then use our formula from unit 2 to get here 32.1 grams. And then lastly, it says how many molecules of gas are present. Well, we go back to the Avogadro number formula. We've got 2 moles that we calculated in part A. We multiply it by the Avogadro number to get 1.20 times 10 to the power of 24 molecules of CH4. Okay, so here is we're using the ideal gas law. So use the ideal gas, and sometimes I'm not going to state that you're going to be using the ideal gas law, but in this question we happen to use it. So we're referring to calculate the molar volume. Now, don't be fooled by the term molar volume. Okay, It really means find V. Find V if N is equal to 1 mole. Because remember, the units for molar volume is this: liters per mole. This per mole means per 1 mole. Right? It's just like kilometers per hour. What's the distance that's going to travel in 1 hour? That's your speed. Okay, so that's what that per mole means. So it's referring to 1 mole. So don't be fooled or scared by some of the terminology. Okay, that's why it's important that you do understand this. If you're cramming last minute, it's not going to help, because you're going to be overwhelmed by all the little pieces that you might be coming into this lesson that you're missing out on. Anyhow, so we best bet, as I said, when we were talking about the Boyle's Law, Charles Law, Gay-Lussac's Law, list the numbers that you're given, right? Because if you look at it like, oh, okay, this question is asking me to find V. I've got P, I've got T. So it's not combined gas law, because it's not giving me an initial and final state, right? And so, I figured out that there's 1 mole. So this looks like the formula: PV is equal to nRT. So here we've got the formula: PV is equal to nRT. We isolate for V, right? Throw in all my numbers, substitute all my numbers, and divide, and finally get 24.8 liters. Okay, so there is the molar volume of a gas. And now here's the thing, one thing to make note: at standard ambient temperature and pressure, SATP, I happen to give it to you here, but remember that at SATP, that T is equal to, T is not 0, T is 25 degrees Celsius, and P is 100 kilopascals. Okay, so remember that, that's SATP, while STP, T is 0 degrees Celsius, and P is equal to 101.3 kilopascals. Okay, and we're just going to quickly go to this this last one here. Typically, I don't give these ones on an evaluation, because one of the things here I ask is to find the volume of a cylinder. But anyhow, we are isolating here to find the number of moles, right? Using our ideal gas to find the number of moles. Once we have that, then we can find the mass. Okay, and there's our mass, but in order to find the volume that we found here, we would need to find the volume of the cylinder. But anyhow, understand that I could be asking you in a question, find the number of moles, and then taking that number of moles and finding the mass of something. So just be aware of what kind of questions. Again, please do the practice problems, do the homework questions that I have outlined on my website. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.